Our entire world is connected through types of energy, and we would not survive without it. At the core of it, our energy comes from the sun, and I'm not just talking about solar panels. It could be from the food cycle with plants getting their energy from the sun, herbivores getting their energy from plants, and then us getting our energy from both of these sources. Some of the earliest representations of energy were embodied by the Latin term vis viva, meaning living force. However, in 1802, Thomas Young was the first person to replace the term vis viva with energy, and Sadi Carnot and William Rankine further refined this into the modern concepts of heat, work, and different types of energy. The definition of energy as we know it today is a quantity used to describe the ability or capacity to do work, with the SI unit for it being joule J, with 1 joule equaling 1 kilogram times meters squared divided by seconds squared. Work refers to the transfer of energy between objects or systems when a force is applied over a distance, with the equation work equals force times distance, and is measured in joules as well. The transfer of energy through work can be from either kinetic energy or potential energy. The easiest way to remember kinetic energy is by associating the term kinetic with movement. This movement can be from vibrations, such as when you heat up food in a microwave, the water molecules in the food absorb the microwaves and begin to vibrate, and then that is converted to thermal energy, which heats your food. The other is rotational movement, like a baseball being thrown. We can measure the amount of kinetic energy an object like a baseball has with the equation E kinetic equals 1/2 mass times velocity squared. For fun, let's calculate the kinetic energy of a baseball at 50 miles per hour versus 100 miles per hour. The approximate weight of a baseball is 0.15 kilograms. Remember, we must convert all the units to the units that match joules, namely kilogram times meters squared divided by seconds squared. 1 mile per hour equals approximately 0.447704 meters per second, so the two equations would look like 0.5 times 0.15 times 50 times 0.44704 squared equals 37.47 joules, and 0.5 times 0.15 times 100 times 0.44704 squared equals 149.88 joules. Because the velocity is squared, even though one baseball is moving twice as fast as the other, it has 4 times as much kinetic energy. Potential energy is almost the opposite of kinetic as it pertains to objects at rest. The best way to think of this is that these objects potentially have energy, such as the book on a shelf. If that shelf breaks, that book is coming down with energy. There are multiple forms of potential energy, such as gravitational potential energy, the book example, elastic potential energy, energy associated with springs, chemical potential energy, energy in chemical bonds, and electric potential energy, energy from charged particles. Let's go over the two most common equations relating to potential energy. The first is E potential equals mass times gravity times height. Hopefully that one is pretty straightforward. Think of the book example. The second relates to the electric potential energy, ELP, and is critical when dealing with charged atoms, molecules, or ions, and the equation is ELP equals K times Q1 times Q2 divided by D, where K is a charge constant of 8.99 times 10 to the 9th joules times meters divided by coulombs squared. Q1 and Q2 are the electrical charges of the specific species you look and calculate, and D is the distance between the species. I hope this explanation helps, and if you have any further questions, feel free to ask. If you found value in the video, please like it and let people know about the channel because it really does help spread the knowledge. Based on what you learned, think about the following questions. Calculate the kinetic energy of a 7-kilogram bowling ball rolling at 15 miles per hour. Hint, 1 mile per hour equals 0.44704 meters per second. And calculate the electrostatic potential energy of 2 electrons 53 picometers away. Hint, the charge of an electron is negative 1.602 times 10 to the negative 19th coulombs, and a picometer equals 1 times 10 to the negative 12th meters. Thermodynamics is a branch of physics that deals with the relationships between heat, energy, and work, thereby studying the principles governing the behavior of matter and energy transformations in various systems. The first law in thermodynamics is the law of conservation of energy, which states energy cannot be created or destroyed in an isolated system, but it can change forms, transferring between the system and its surroundings. Therefore, all the forms of energy we learned about in Unit 5.1 can be interchanged, but the energy itself is never destroyed. Now let's see how this law plays out in real-world scenarios. Remember, energy exists in two main forms: kinetic energy associated with motion and potential energy associated with position. Now let's imagine these energies at play within a system with exothermic and endothermic processes. Picture a chemical reaction where bonds are broken and formed. If the overall result releases energy into the surroundings, it's an exothermic process. A great example of this is fire. Fire, also known as combustion, is a type of exothermic reaction which occurs when a substance reacts with oxygen, releasing energy in the form of heat and light. During combustion, chemical bonds in the fuel, such as hydrocarbons in wood or gasoline, break as the fuel combines with oxygen to form new bonds in combustion products like carbon dioxide and water. The overall result is a release of energy driven by the rearrangement of the chemical bonds. The first law tells us that even though the chemical bonds change, the total energy within the system and its surroundings remains constant. Now consider a process where energy is absorbed from the surroundings. This is an endothermic process. For this, let's use the example of the melting of ice that involves the absorption of heat from its surroundings. This is considered a phase transition in which the solid ice, a well-defined structure of water molecules held in a crystal lattice, transforms into liquid water. During melting, the water molecules are held together by strong hydrogen bonds and other intermolecular forces. As heat is applied, this energy breaks these intermolecular forces between the molecules in the ice lattice. The absorbed energy increases the kinetic energy of the water molecules, which disrupts the organized structure of the solid crystal lattice. Once the kinetic energy overcomes the intermolecular forces holding the molecules together, the ice transitions to a liquid state. The water molecules are now free to move around each other, resulting in the characteristic flow of water. Keep in mind that the energy is absorbed from the surroundings, which therefore causes the surroundings to cool. This phenomenon is fundamental to our everyday experience, such as when ice melts in a drink. Despite the system taking in energy, the total energy is equal and conserved, therefore ensuring the first law. Whether it's an exothermic reaction warming your hands or an endothermic reaction cooling a beverage, the first law is always at work, ensuring the total energy of the system and its surroundings remains constant. I hope this explanation helps. And if you have any further questions, feel free to ask. If you found value in the video, please like it and let people know about the channel because it really does help spread the knowledge. Based on what you learned, think about the following question. Label each of the following as either endothermic or exothermic processes: the evaporation of sweat, freezing of water, human breathing, dissolving salt in water. Today we're going over enthalpy in chemistry. If this piques your interest, let's be real, this doesn't pique anyone's interest, but stick around because it is essential to understand to be an exceptional chemist. For example, modern air conditioning or refrigeration wouldn't be possible without the understanding of enthalpy. These systems rely on the transfer of heat, enthalpy, to create a cooling effect. Essentially, they're on vapor compression cycles, which use a refrigerant that undergoes phase changes from liquid to gas and then back to liquid in a closed system. During these phase changes, the enthalpy of the system changes significantly, allowing for the absorption and release of heat. We'll go over the specifics of AC with a great example of its cooling effects later in the video once enthalpy is explained a bit more. In my opinion, the best and simplest way to think of enthalpy is to associate it with heat. However, technically, heat is defined in the equation for change in energy with delta E equals Q plus W, where Q equals heat added to or taken from the system, and W equals work done by or on the system. Enthalpy in chemistry is a measure of the total energy of a thermodynamic system. It includes the internal energy and the energy established from pressure acting on the system's volume. Enthalpy is a state function, a property that only depends on a system's current condition, not how it got there, like temperature or pressure, and is denoted by the symbol H. I find it easiest to remember it being H by emphasizing the TH in enthalpy. It's defined as H equals E plus PV, where H is enthalpy, E is the internal energy of the system, P is the pressure of the system, and V is the volume of the system. Enthalpy is particularly useful in scenarios where pressure is held constant, such as in many chemical reactions happening in open containers in laboratories, because under constant pressure, the change in enthalpy, delta H, equals the heat absorbed or released by the system. This is why I particularly think of it as heat. Let's prove this through some equations. The equation when pressure is constant is delta H equals delta E plus P delta V. When we insert our previous equation of delta E into this, we get delta H equals heat plus work plus P times delta V. According to the pressure volume work equation, which relates the work done by or on a system during a volume change under pressure, W equals negative P times delta V. Plugging this into the delta H equation, we just get delta H equals Q heat. So the change in enthalpy is heat. However, pressure has to be constant. Now that we know a bit more about enthalpy, let's go over the air conditioning example. As stated previously, AC works on vapor compression cycles, which use a refrigerant that undergoes phase changes that facilitates the transfer of heat. The key stages of the cycles where enthalpy plays a cooling role is in the evaporation stage, similar to sweating. Inside the evaporator coil, the liquid refrigerant absorbs heat from the environment like water in a glass that gets warmer and evaporates, turning from a liquid to a vapor. This process involves a significant increase in enthalpy as the refrigerant absorbs heat, resulting in a cooling effect on the surrounding area. So let's look at the numbers behind a typical AC unit. The enthalpy required to change propane, a highly efficient refrigerant, from liquid to gas at its boiling point of negative 42.1 degrees Celsius or negative 43.8 degrees Fahrenheit, is about 428 joules. But that doesn't really tell you much about temperature changes, so we need an equation for that. The formula to calculate the change in temperature, delta T, when a certain amount of heat, Q in joules, is added or removed from a mass, M in grams, of a substance is delta T equals Q divided by M times C, where C is the specific heat capacity in joules per gram, which is 2.22 joules per gram Kelvin for liquid propane. Plugging these numbers into the equation for 20 grams of propane, this might not seem like much, but in its gaseous state, it's approximately 10 liters. Delta T equals 428 divided by 20 grams times 2.22 joules per gram Kelvin equals 9.64 degrees Kelvin, which equals degrees Celsius. Converting that to Fahrenheit is close to 50 degrees. This change of approximately 10 degrees Celsius or 50 degrees Fahrenheit is what allows the refrigeration to work, because the AC unit can blow air over the colder propane, which cools that air that then pumps into your room. Keep in mind that this is just one stage. The gaseous propane needs to be condensed down to a liquid so the cycle repeats. To do this, the vaporized propane is compressed by a compressor, which increases its pressure as well as its temperature, which the AC unit needs to get rid of. To do this, it sends the hot propane to a condenser where the propane transfers its heat to air that is then pumped outside. That is why on any AC unit, there is also a discharge of hot air, or the AC unit itself feels warm. From there, the high-pressure liquid propane passes through an expansion valve back to the evaporator coil, where its pressure drops suddenly, leading to a decrease in temperature and enthalpy to start the cooling process again. All of this might seem like it doesn't relate to chemistry at all, so why then talk about it? I'm bringing this up because during a chemical reaction, there are changes in the heat exchange of the molecules, which we call enthalpies of reactions, sometimes referred to as heat of reactions. Chemists define this as delta H equals H products minus H reactants, where H products is the total enthalpy of the products and H reactants is the total enthalpy of the reactants. There are several types of enthalpy changes associated with chemical reactions. Some of these include enthalpy of formation, delta HF. This is the heat change that occurs when 1 mole of a compound is formed from its elements in their standard states. Enthalpy of combustion, delta HC. The heat change that occurs when 1 mole of a substance is completely burned in oxygen. Enthalpy of solution, the heat change associated with the dissolution of a substance in a solvent. Enthalpy of neutralization, delta H neut. the heat change that occurs when an acid and a base react to form water and a salt. Enthalpies of reactions are used in chemistry for a variety of important purposes. Some of these include predicting the reaction feasibility or determining exothermic/endothermic reactions. For this, chemists assess whether a reaction is exothermic, delta H is less than 0, or endothermic, delta H is greater than 0. Using these, chemists can gauge the spontaneity of a reaction under certain conditions, although entropy and temperature also play a significant role in determining spontaneity through Gibbs free energy, which we'll discuss at a later time. Energy management. Understanding energy changes in chemical reactions allow chemists and engineers to design processes that are energy efficient, either by minimizing energy input for endothermic reactions or harnessing energy released from exothermic reactions. There are some safety considerations. Knowing the enthalpy changes can help in assessing the risk of thermal runaway exothermic reactions. Reaction optimization. In industrial chemistry, understanding enthalpies helps in optimizing reaction conditions like temperature and pressure to maximize the yield and minimize energy consumption. Chemical bond analysis. Changes in enthalpy can give insights into the strength of chemical bonds formed and broken during a reaction. This contributes to a deeper understanding of molecular interactions and even helps with understanding of reaction mechanisms. The study of enthalpies of reactions is fundamental in both theoretical and applied chemistry, enabling scientists to predict, control, optimize chemical reactions for various practical and research purposes. I hope this explanation helps. If you have any further questions, feel free to ask, and if you found value in the video, please like it and let people know about the channel because it really does help spread the knowledge. Based on what you learned, think about the following question. When can you associate enthalpy as heat? Welcome, ladies and gentlemen. Today we're going over how scientists measure heat in chemistry. Have you ever touched metal that has been baking in the sun? It's so much hotter than anything else, right? This is for various reasons, but one of them is due to a property which we call heat capacity C, which is the amount of heat required to change the temperature of the system by 1 degree Celsius. Delving further, if you compare the heat capacity of iron versus water, we find that water has a heat capacity that is roughly 9 times higher than that of iron. This means that water requires much more energy to change its temperature compared to an equal mass of iron, which is one of the reasons why an iron pole is so much hotter than a puddle. Interestingly, the high heat capacity of water is one of the reasons that life on Earth is possible. The vast multitudes of it is what keeps the temperatures on Earth more constant than other planets because it can absorb the heat from the sun without getting extremely hot itself. Now back to heat capacity. Scientists measure the change in heat, delta H, in chemistry through a process called calorimetry that measures the amount of heat absorbed or released during a chemical process via the use of a calorimeter. There are various types of calorimeters, but the most common ones include a coffee cup calorimeter for constant pressure. Remember, delta H equals Q, or heat, when pressure is constant, and a bomb calorimeter for constant volume calorimetry. In their simplest form, both of these calorimeters consist of a reaction vessel inside a water bath. The vessel contains the reactants, and the water bath helps measure the temperature changes. When the reaction occurs, the change in temperature of the water is used to calculate the heat transferred via a thermometer. As talked about previously, the calorimeter and the substances inside it have a known heat capacity, C, which again is the amount of heat required to change the temperature of the system by 1 degree Celsius. Thinking about it deeper, a glass of water heats up much higher throughout the day than a swimming pool, right? This is because more massive substances can absorb more heat, so we have to control for mass. Scientists came up with a refined term called specific heat capacity, or specific heat, which is the heat capacity of 1 gram of the substance, denoted by CS. There is also molar heat capacity, cm, that is the heat capacity of 1 mole of substance. To measure this change in heat, Q, 1 gram of a substance at constant pressure, the coffee cup calorimetry, scientists use the formula Q equals CS times M times delta T, where CS is the specific heat capacity of the substance, M equals mass, and delta T equals the change in temperature. Keep in mind you can rearrange this formula algebraically for a chemistry experiment to solve for any of these values if they're unknown and you have the others. For constant volume heat change calculations, we use bomb calorimeter, which is similar to the coffee cup example, but think of it as we took that cup, sealed it, and placed it in a water-filled sealed container so pressure is constant. Bomb calorimetry is most often used for combustion reactions, and the water still absorbs the heat and is measured to calculate the change in heat. The formula for bomb calorimetry is Q equals negative Ccal times delta T, where Q equals the change in heat, delta T equals the change in temperature, and Ccal is the heat capacity of the entire calorimeter, therefore adjusting for the mass. Over the years, scientists have tabulated the various calorimetry calculations and found out that they're usually able to calculate delta H for any reaction from other tabulated delta H values, thereby saving time and not having to do all the calorimetric measurements. This led to the discovery of Hess's law, which is a principle in chemistry that states the total enthalpy change for a chemical reaction is the same regardless of the pathway by which the reaction occurs, provided the initial and final conditions are the same. Simplifying this law implies that the heat released or absorbed in a chemical reaction is constant whether a reaction takes place in one step or multiple steps. Hess's law is particularly useful in thermodynamics for calculating enthalpy changes delta H for reactions where direct measurement is often difficult. It allows chemists to infer the enthalpy change of complex reactions by combining simpler reactions that are easier to measure or are already known. This is because the enthalpy change for a chemical process is dependent only on the difference between enthalpy of the products and the reactants and not on the specific pathway taken. An example of Hess's law is in the combustion of graphite to form carbon dioxide, C solid plus O2 gas going to CO2 gas. Direct measurement of this reaction's delta H might be challenging. However, if the delta H for the formation of carbon monoxide from C and the delta H for the oxidation of carbon monoxide to carbon dioxide are known, these reactions can be combined to represent the total overall reaction. C plus 1/2 O2 going to CO is delta H1. CO plus 1/2 O2 going to CO2 is delta H2. The overall reaction is the sum of these two steps, and the overall delta H is the sum of delta H1 and delta H2. This approach demonstrates Hess's law since it doesn't matter how CO2 was formed from carbon and oxygen. The total enthalpy change will be the same. The tabulated delta H values also lead to the idea of enthalpy of formation, delta HF, often referred to as heat of formation, and when used in conjunction with Hess's law, this is a powerful tool for scientists. The enthalpy of formation is a thermodynamic quantity that measures the change in enthalpy, total heat content, when 1 mole of a compound is formed from its constituent elements in their standard states at a pressure of 1 atmosphere, atm, and a specific temperature, usually 25 degrees Celsius, 298 Kelvin, where it's most stable. Let's go through an example. Consider the formation of water H2O from its elements hydrogen H2 and oxygen H2. Both in their standard states, the equation looks like 2H2 plus 2O2 going to 2H2O. The delta HF for H2O is approximately negative 285.8 kilojoules per mole, indicating that the formation of water from hydrogen and oxygen gas releases 285 kilojoules of energy per mole of water formed, since elements in the pure state release 0 kilojoules. This negative value signifies an exothermic reaction where heat is released to the surroundings. By the way, this is the concept behind hydrogen-powered vehicles. Considering what we know about Hess's law and that enthalpy change for a chemical reaction is the same regardless of the pathway which the reaction occurs, we can therefore calculate the enthalpy change of a reaction based on the enthalpies of formation. The enthalpy change for a chemical reaction can be calculated using the enthalpies of formation and the following equation. Delta H reaction equals the sum of delta HF of the products minus the sum of the delta HF of the reactants, where the sum of delta HF of products equals the sum of the standard enthalpies of formation for all the products, each multiplied by its coefficient in the balanced chemical reagent, and sum delta HF of reactants equals the sum of the standard enthalpies of formation for all reactants, each multiplied by its coefficient in the balanced chemical equation as well. Let's go through an example with our handy combustion of methane. The equation for the combustion of methane is CH4 gas plus 2 oxygen gas going to CO2 gas plus 2 H2O liquid. Now we need to sum the delta HF of the reactants and products. Since we have the tabulated data, we know that the delta HF of CH4 methane equals negative 74.8 kilojoules per mole. Delta HF of oxygen equals 0 kilojoules per mole. Since oxygen gas is in its standard state, therefore 0. Delta HF of CO2 gas equals negative 393.5 kilojoules per mole, and delta HF of H2O is negative 285.8 kilojoules per mole. Plugging these values into the equation looks like delta H reaction equals 1 times negative 393.5 plus 2 times negative 285.8 minus 1 times negative 74.8 plus 2 times 0 equals negative 890.3 kilojoules per mole. By the way, that's 3 times more than the combustion of hydrogen. I hope these explanations help. If you have any further questions, feel free to ask, and if you found value in this video, please like it and let people know about the channel because it really does help spread the knowledge. Based on what you learned, think about the following question. Calculate the enthalpy change for the combustion of octane, the main component of gasoline, given the following information. The balanced chemical equation is C8H18 plus 12.5 O2 going to 8 CO2 plus 9 H2O. The standard enthalpy of formation values are for C8H18, negative 250.1 kilojoules per mole, CO2, negative 393.5 kilojoules per mole, H2O, negative 285.8 kilojoules per mole, and oxygen, 0 kilojoules per mole. Might be the single most important issue for the human race to solve in the upcoming decades. We're first going to discuss how we as humans get energy in the form of food, and then get into fuels we as humans use to power our lives. There are 3 main categories that most humans get their energy from. A fourth, if you're an alcoholic, which are carbohydrates, fats, and protein. However, regardless of the category, they're all converted into acetyl-CoA by your body, and this is the molecule that your body uses to produce the energy that heats your body and allows you to move. The difference between the carbohydrates, fats, and protein is their energy density. Similarly to how methane, the main component in natural gas, produces approximately 3 times the amount of energy per mole than hydrogen does, a gram of fat provides 9 calories per gram, while carbohydrates and proteins provide 4 calories. But what about our alcoholic? They get 7 calories per gram from alcohol. Now onto the fuel that powers our lives. There are 5 main sources of fuels that humans use for energy. They are nuclear, renewable, petroleum, coal, and natural gas. To get a better grip on their utilization, let's look at a rough estimate of their use in the United States by percentages. Nuclear energy, used almost exclusively for electric power generation, accounts for about 8 to 10%. Renewable energy, consisting of biomass, hydroelectric, wind, solar, and geothermal energy, contributes to 12 to 14%. Petroleum, used mainly for transportation, accounts for approximately 35 to 37%. Coal, used mainly for electricity generation, accounts for about 12 to 10%. Lastly, natural gas, used for heating and power generation, accounts for about 32 to 34%. We'll be going over through each of these more in depth in the upcoming units, and I have a couple shorts out now or coming out soon that go into nuclear fission and fusion in much more depth. I hope these explanations help. If you have any further questions, feel free to ask. And if you found value in this video, please like it and let people know about the channel because it really does help spread the knowledge. Based on what you learned, think about the following question. Calculate the percentage of calories that come from fat, protein, and carbohydrates from one Oreo that has 3.5 grams of fat, 10.5 grams of carbohydrates, and 0 grams of protein. Thank you so much for spending your valuable time learning and bettering yourself. If you like the video and want to learn more, donate, or get tutoring, please check out my website, nocollegeneeded.org. You can use the code NCN for 20% off tutoring and any supplemental materials. If the subject isn't up yet, please be patient. I'm working on bringing them up as soon as I can.